Yeah, does it work now? And
Yes, I will share the screen itself and then go to the presentation to avoid moving between windows.
yeah, great. So Dr. Ahmed Shawky Moussa is a professor of computing and computational sciences at Cairo University. He has work and talks around HPC, large scale simulations, AI, and quantum computing. He's also president of OTIMI Systems Company, OSC LLC. Dr. Ahmed also teaches mainly physics simulations and computational physics simulations, and worked as a consultant for major industrial partners and enterprises, mainly on how to integrate HPC and also advanced scientific computing and super computers. Yeah, the floor is yours, Dr. Ahmed.
Thank you, Dr. Taha. All right, I'm talk today about the nexus between high-performance computing, AI, and the quantum computing and quantum technology. I'm glad we started the lecture a little bit early to make some use of the time. Sometimes things take more time than you expect. Okay, I will start. I will start by showing this picture. I usually make this start often when I talk about high-performance computing. This computer is called Jaguar. It was designed and built by Seymour Cray, Cray Company, and this is the company that HP actually acquired in order to get into the world of HPC and supercomputers, because they could not jump in from scratch and catch all the progress running in this very important area. This computer was the fastest computer in the world. It was built at Oak Ridge National Laboratory over about 5,000 square feet. And overall, it is you divide by 10 to get the square meter equivalent. So you can say that it is approximately 500 square meter surface area. You can see how big it is. This was the fastest computer in 2009. Only 2 or 3 years later, I think about 2011 or 2012, this became the fastest computer in the world. It was called K, and it was by Riken University with in Japan. As you can see, it was using nearly 90,000 computer processors and almost equivalent area to the Jaguar that we have seen before. But the racking, which we call the rack design, is different here. The racks are separated on the front, and you can see the air conditioning on the raised floor. This is a very important area in the design of computing systems. After this became the fastest computer in the world in 2011 or 2012, the same university, Riken, with the same company, Fujitsu, found that K was not good enough, was not fast enough, and they built Fugaku to become the world's fastest computer in 2019. You see the progress, how the progress is, the competition is very strong in this area. And it is definitely not spending these billions of dollars just for the competition for showing off. It is actually for a gain and for important reasons that we will get a glimpse for in a few minutes. This was the Fugaku computer that became the fastest, and at that time they actually scrapped the K computer, which was few years earlier the fastest computer in the world. These are the specs of the Fugaku computer. It uses more than 7.5 million cores. It consumes nearly 30 megawatt hour, and this is the R peak and R max. R peak is the theoretical speed of the maximum speed of the computer, and R max is the practical or the benchmark maximum speed of the computer, and these are the specs. You can get all these details and more if you go to the top500.org. Just type top500.org and you get all the details of all the top 500 computers in the world. After that, in about 2021 or 2022, this became the fastest computer in the world. It's called Frontier, and it was built by HP. And as I said, HP, to get into this area years ago, they actually acquired Cray Incorporation to get all the knowledge and know-how and get to compete in this area. This was what we call the first exascale computer. Exa means 18 zeros. It means 1,000 trillion operations every second. Until the previous one here, it was in the peta scale. Peta means 15 zeros, which is 1,000 trillion operations per second. Here it became million trillion floating point operations every second. As you can see, it uses more than 20 megawatt hour of energy. It has nearly 9 million cores, and this is the maximum practical speed, 1.1 exa flops. It didn't stay the fastest for long because 2 years later, this appeared El Capitan. It became the fastest supercomputer in the world with number of cores more than 11 million cores, and the practical speed was 1.7 exaflops, means 1.7 times million trillion floating point operations every second. This is the speed, and this is the energy it consumes. It's nearly 30 megawatt hour. As you can see, it is not a linear relationship. So when you increase the number of cores, you don't necessarily increase the number of the parameters of performance linearly. Also, when you increase the power consumption, you don't get equivalent power. It is very complicated area to study. Before we tap into this, let's see this. We are trying to answer the question, why would we need computers of this speed? And actually, it's still not enough. You can see that every year or every 2 years, we get the top supercomputer or the fastest supercomputer in the world. And in a few months, you get an even faster one. And we are still running now for what we call the zeta scale. So we just got into the exascale a few years ago, maybe 4, 5 years ago. And now we're shooting for the scale. Zeta is 1,000 exa, which means trillion operations every second. So the question is this: why would we need these speeds? Look at this article by IBM and look at this date. It was in 2012. They were the first exascale computer appeared in 2022 or 24. But IBM at 2012 was talking about this. We must, it's not that we have to, we must build an exascale computer before 2024. So this was a must for them. Why is that? For many reasons, actually. We will talk about that further in a minute. But this was only one example. The picture that we see here is a telescope. Not all the telescopes or the space probes can be sent to fly in the space like James Webb or Hubble or Voyager or any of these. Some of them are too big to do that, so they have to be installed here on Earth. So this telescope is installed over 3,000 kilometers square, and it's not optical telescope. It is a telescope of sensors to collect data from the deep space, trying to look at the origin of the universe. This telescope alone is generating exabytes every day. So if we do not have an exascale computer these exabytes will accumulate and will be useless, despite the fact that we will be looking for where to store them. So this was just one example of the many examples that necessitates the need for exascale computers, and show us why IBM was talking about we must have an exascale computer, and that was in 2012, and they wanted to get it before 2024 because this was actually the time for launching this telescope. The world was working, several countries together were collaborating, trying to get this telescope to work by 2024. And 12 years earlier, they were trying to build the computer that will process the data for this. This is why actually I know that in the media everybody is talking about AI, but actually in the political room, in the decision makers room, the talk is more about high performance computers because AI to work, it needs a vehicle to ride on. That vehicle is HPC. It is high performance computing. And this is why the White House, for example, after a public speech by President Barack Obama, and that was in 2015, we see that the first exascale computer appeared about 7 or 8 years later. But at 2015, President Barack Obama spoke about the necessity. It is a matter of national security, life and death, that the United States must not only acquire or have an exascale computer, but must be the first country in the world to have an exascale computer. And he spoke about the fact that every day a country is behind another country in the exascale. That means that country is getting uh, 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 pushed back or retarded by 100 years for every day. And this is why it was a matter of national security to have an exascale, not only to have an exascale, but to have the first exascale computer in the world. And after that, the next day, he actually inaugurated this White House executive order for the National Strategic Computing Initiative to have the first exascale computer. And 7 or 8 years later, indeed, they got the first exascale computer, which was Frontier. Today, we have about four exascale computers, three in the United States and one in Germany. And if you want to see the list, it is again on top500.org. You can see all the top 500 computers in the world. Now, somebody might ask, well, we had petascale computers before that. At the time, IBM spoke about this, and the time President Barack Obama spoke about this. We had petascale computers, and EXA is 1,000 peta. So why don't we get a computer 1,000 times bigger, and that will be an exascale? It's as simple as that. Of course, a naive approach to this problem would be that way, but let me show you why this is not a practical approach. As we have seen here, we were talking about Jaguar. It was on almost 500 meters, 500 square meters. So when we're talking about multiplying this by 1,000, it will become 500 kilometers square. Imagine you want to install a single computer on 500 kilometers square. Difficult, yes. Very difficult, miraculous, all this is yes, but it's still doable. We can allocate 500 kilometers square for a computer if it is that necessary. But the real problem is here. These are the computers from number 6 to number 10 on the top 500. And what is most important here is this column. This column is the energy consumption of these computers. We can see, exclude this one for a minute, but you can see here that it is about 7 megawatt hours for a thousand. It means that you want to get this is 7 mega, so you want to get 7 gigawatt hour to get the computer to run. You know that a nuclear reactor, an average nuclear reactor or typical nuclear reactor, generates 1 gigawatt. So for this computer to work, if we get it to, if we multiply by 1,000 and try to get it to work as an exascale computer, it will need 7 nuclear reactors to be only the battery of that computer. We cannot afford to do that. The Earth itself as a planet cannot afford to do this. So the difficulty during the previous 15 years trying to develop the exascale computer was to re-architect, change many technologies and approaches and algorithms to get it to work with a reasonable amount of energy. And that reasonable amount of energy was introduced by the Department of Energy in the United States to be a maximum of 20 megawatts. So they set that condition. If you want to get an exascale computer working, you have to make that computer no more to consume no more than 20 megawatts. And this is what they were working on. And yet, even they made it 20 megawatts, but they still could not actually comply with this. As you can see, the top computers here, they exceeded the 20 megawatts. The top one here is nearly 30 megawatts right now. And we still have the same problem to get the zeta scale. Imagine the zeta is a 1000 exa. So imagine that you have a computer that is 30 megawatts and you want to multiply it by 1,000. Uh, um, so so it's 30 times the sound, so it's a 300 gigawatt. So you probably need about 300 nuclear reactors to power one computer. Of course, this is impossible and unacceptable. I think Japan is the closest one to get to the zeta scale, but I hope this part showed you a little bit of a glimpse into the fierce competition in this direction. Countries are spending hundreds of billions of dollars in this competition, not only to get a fast computer, but they want to get a faster computer. And this is definitely not just to show off. It is actually to get some gain about that. Let's now move to the AI. I said before that AI rides on top of HPC. So one of the reasons we want to get the fastest computer in the world is to be able to compete and be ahead in the AI. This is one of the very important. Without it, you cannot run machine learning model training. You cannot be ahead in the AI era. So this is actually the vehicle, or you can say the driver of the AI, along with all the military, the biomedical, the financial, and all the other sectors. Now, when we look at the AI, we usually see this picture um, depicting what AI is. This picture is actually true, but I claim that it is inaccurate. I know these days most people think that AI is machine learning, and more specifically deep learning, which is not true. It is true, but it's inaccurate. Why is it inaccurate? Because the machine learning part and the deep learning part are smaller part of the AI than that. AI is wider. It encompasses many other areas, especially computational intelligence and how to compute intelligently, how to deal with, capture, and compute the uncertainty in the real world, in the systems. And that may take a different talk, a separate talk by itself. So AI is not only learning, as most people think nowadays. It includes learning, comprehension, problem solving, decision making, creativity, and autonomy. All these are branches of the AI. The systems, the computational systems leading to implement this are also too many. They are not limited to machine learning and deep learning as most people think. But since we spoke about the energy, this is really odd and ironic. Let's look at this problem. You know that especially those who worked on machine learning training, machine learning models, know that they always complain about not having enough GPUs or strong enough GPUs to run their models. They want to run them for longer time. They need to take more energy. So they always claim that they need better machines. Typical training of a large AI model like ChatGPT-4, for example, it takes between 10 to 100 megawatt hour for quite some time. This, of course, dissipates heat. It requires cooling, grid management. It's all the problems of the energy associated with this. When you finish training, you get the inference. So the inference doesn't take as much power. You can actually install the inference on your mobile phone, but it is the training that consumes this much power. So one of the things that we do the training for is to do predictive modeling. And one of the things that we do predictive modeling for is actually the forecast of energy consumption. So we want to train a model, spend all this energy to train a model to forecast the energy consumption of certain systems in order to save some energy. Are we really saving energy? So this is why I'm making it with a funny face, because to train the model, you need about 100 megawatt hour for quite some time. And then after that, you want to save some energy using this model. Would the energy you are saving be worth spending this 100 megawatt hour spending on on training the model? We don't know. We don't have the answer for that, because of course when we train the model, we train it for other purposes as well. But the trade-off is not yet calculated. Nobody knows whether we are really saving energy or wasting energy by training these models in order to make predictive modeling of the energy consumption. The amount of energy that we use for training a large AI model, that GPT-4, for example, it can power hundreds of homes in the United States. This was calculated. So should we power hundreds of homes or train an AI model? This is actually an open area. Part of it is still philosophical, but part of it is still a real calculation for us. What we see in here now, when we're talking about the energy and power, is Gordon Moore, co-founder of Intel, and the guy very famous for Moore's Law. Actually, Moore's Law is not a law. It was a prophecy or a prediction. He predicted that the number of semiconductors are going to double every 18 months, and it worked exactly as he said for quite some time. And this is why they turned it into what we call a Moore's Law. At a certain point, the progress of Moore's Law did not proceed as it used to. And this was because of two problems. We call them, in computer science, we call them two walls. One of them is the memory wall. The reason for that is speed of CPUs were going much faster than the speed of memory. Why? We don't know exactly, but this is what people are guessing, is that it is market driven. Who asks for the speed of the memory when you buy a RAM chip? You never ask for the speed. You always ask for the capacity. This is why the industry is trying to make larger memory. But when you get to the CPU, you are always asking for the speed. So the industry is trying to get faster CPUs. This, after a while, it was not significant in the beginning, but after a while, it created a large gap between the two, and the memory was not able to supply the necessary instructions and data for the processors to perform. The second one is what we call the power wall. At a certain time, the clock rate was speeding up along with the power growth. And then at a certain time, we were not able to speed up the clock rate anymore until now, until today. Those students that I was teaching early in 2005, for example, 2007, around that time, I used to tell them in the computer architecture course that in a year or two, we will not get any faster processors than what we have now. And right now, I tell my students, for the past 15 years, we haven't been getting faster processors using the traditional way of speeding up the processor by speeding up the frequency. So at a certain point here, we're starting reducing the power again and keeping the clock rate the same in order to speed up. Why is this? Because of what we see. The energy consumption that we talked about before is proportional to the capacitive load and the voltage squared. This is actually the exact formula. It is half the capacitive load times the voltage square. So this is the energy. If we want to get the power, we multiply that by time to get the frequency, which is the frequency of the processor. It's what we call the clock rate. So this is the exact equation of the clock rate. Why is this a problem? Because this is the power. For quite a while, as you can see, the voltage is used in the equation squared. For quite a while, we were getting the zero in the voltage circuit by picking up a zero voltage. And we are getting the one by picking up a 5 volt. So 5 represents 1 in the numerical system, and 0 represents 0. But you know, it is never exactly 5 and never exactly 0. So when you say 0, it's not that 0. There is some noise, some jittering around the 0. And when it is 5 volts, it's never 5 like this. It is jittering around the 5. At a certain point, we were able to reduce the 5, which is coming into the equation with 25. We made it 4. So now it is coming into the equation with 16. So what do we do with this difference? Do we lower the power? We didn't want to lower the power. We wanted more speed. So instead of lowering the power, we actually used that difference to increase the frequency. And then the 4 became 3. So we increased the frequency again. And then it became 2. We increased it. So whenever we are able to reduce the voltage representation, we use that difference to increase the frequency until we reached a point where we were unable to reduce the voltage anymore. Because when we reduce it more than that, the 0 and 1 actually conflict with each other. So you get wrong calculation. The only solution to that was to keep it up and try to increase the frequency, and that caused the CPUs to burn out. And this was the time that we reduced the frequency again. So this was about 3.7 gigahertz. It was the maximum we were able to reach. So we tried to reduce it again and keeping the clock rate the same and trying to speed up using a different method, which is using the multi-core. So instead of making a larger or stronger processor, we split that into 2 or 4 or more processors. But that actually, this is the details I will, I think I already explained that. So it became, the performance became commensurate or proportional to the number of cores instead of the frequency of switching. But that actually came at a price. It is what we call in computer architecture the new contract. Contract between who? Between the hardware and software people. I know people who studied architecture with me heard me always saying that we need this separation, but let's assume that there is a separation right now just for the sake of the discussion. In the old days, the hardware people told the software programmers, try to write a clean good program, and we will speed it up for you. How are we going to speed it up? We increase the frequency, so it runs faster. But now we are not able to increase the frequency anymore. Instead, we're giving you more code. And now the new contract became up to the programmer. If you write the program using the multi-core, you will get a faster program. No matter what you do, if you write a single line program to run on a single core, you will never be able to speed it up as much as it is not running multi-core, because this is the only way of speeding up the CPUs, the processors right now. So now it became up to the programmer, not up to the processor maker, and this constituted the new contract between the hardware and software people. So now we understand the connection between the HPC and AI. In different lectures, I used to talk more about different areas of applications and different investments, why people spend all these billions of dollars to get the faster computer, but it is not the main topic of this lecture. But before I move to the next subtopic, which is quantum computing, let's look at this example. Suppose you want to run, you want to get a computer to run these trillion operations in 1 second. We said that exascale is million trillion operations every second. So let's say that we are going to run only trillion operations every second, but using a single processor, not using the high performance computing technique. I expect that most of the audience in this lecture know what this is. It's a loop that is going to act on 3 arrays. Each one is trillion elements. So it takes the first element of array X, add it to the first element of array Y, and put the result in the first element of array Z, and repeat that for trillion times. To do that, we will need to have 3 trillion trips between what and what, between the memory and the processor. So here is the processor and here is the memory. So the first trip is to get the first value from X, and then the first value from Y, add them together in the ALU, and then store them in the first value of Z. And these are the first 3 trips only to do the first elements of the 3 arrays. We will do that trillion times. So 3 times trillion trips between the memory and the processor in order to get that. Let's assume that we are running at the speed of light. This is not true. Electrical current is not running at the speed of light, but let's assume that it is the maximum speed in the universe, speed of light. Even if you are running at the speed of light, so now we have the speed, and we want to get the distance. We have the speed and we have the time. The time is 1 second, and we have the speed is the speed of light. So now we want to get the distance. What is the average distance between the memory and the processor in order to get this done in 1 second? The average distance would be 10 to the minus 4 meters. That means that we need to combine a word of memory, assuming the memory is constructed in a square, geometric square, which is not true, but it's close. If it is, then this is the equation to get the distance between the average distance between the average distance of the square, combining a word of memory, regardless of the size of that word, even if it is only 8 bits. You can see that it is a number times 10 to the minus 10 meters, which is the size of a small atom. Not the smallest atom, but it is still a small atom. Even if it is not a small atom, even if it is in a big atom, until comes the day where we are able to store 1 word of memory. You know, the word currently is between 64 bits and 128 bits. Until comes the day we are able to store 64 bits in a size less than an atom, this calculation in 1 second is impossible. And this tells you a glimpse of the complexity and the difficulty of developing high performance computing systems, not only the hardware, but also the software to do that. Now, let's assume that this became possible somehow. We found a way of storing a word of memory in an atom. At that time, this calculation becomes useless because at that time, the calculation is going to be on the quantum level. It will be a subatomic structure that requires quantum mechanics calculations instead of the classical calculations. So the classical calculations are not valid anymore in this case. So one of the drivers toward the quantum computing is that things are getting smaller, 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 and one day they must hit the quantum barrier. So we need to go to the quantum world and use some quantum properties to do calculation. And this takes us to the world of quantum bits. First of all, this is the classical bit. A bit, in the classical sense, uses the Maxwell equation, the Maxwell electricity setup. And if it is off, it is 0. If it is on, it is 1. So the classical computers, including the high-performance computer, use zeros and ones to do everything. They don't understand the assembly language, and they don't understand the high-level language. They only understand these. So we write programs and mechanisms to translate these programs into the zeros and ones because we use classical bits. The quantum bit is not like that. You can see this picture again. It is plain white and plain black. Here, it is at the end a plain black, and the end is a plain zero, but in between there is a gradation between the two. What does that mean? It means that the quantum bit, zero or one or any value in between. The classical bit cannot. It is either a 0 or a 1. And as you have seen, when we reduce the voltage to get them to conflict together, the calculation fails. We cannot do a computer that way. But here, this is the nature of the quantum bit. The quantum bit has to work in this way. You assume that the bit is 0 or 1, or what we call the superposition of the two states over each other. So what we do in the quantum computer is that we get some sort of a particle. It can be electron, photon, nucleus, whatever. And then we apply, expose this particle into magnetic field, north and south. We get it to spin. And then if we place the magnetic field, it becomes 0. If we apply energy to it, it becomes 1, but it's not separated. It gets superposition between the two all the time. We cannot even read it in the middle. We have to wait until it finishes these calculations and then only read the results. So here we apply quantum mechanics. We apply the superposition of quantum mechanics. And this is a problem because quantum mechanics are probabilistic. So any calculation that we do has to be done several times in order to make sure that we got the correct. So we take the average of several times of calculation. And we cannot, in a different talk, I will talk about the Landauer's principle and how it predicted that this is going to be ever increasing energy consumption because it is irreversible computation. But this is the nature. We have to understand that we do not have any way of correcting this. We cannot change it. This is the theory of quantum computing. It's a completely different theory from the theory of classical computers done with the HPC system. So this is the nature of what you have to do the calculation using this. It's the same theory of computability, but it's a completely different theory of computation. However, even though in the beginning you might not feel comfortable with that, you're not used to it if this is the first time you are exposed to it. But let's look at the advantage we get from this. In classical computing, the state that you are likely to get from a classical bit are either 0 or 1. You only have two states. But here you can have, with the two qubits, you can have the 0 or 1, or the superpositions leaning toward the 1, or the superpositions leaning toward the 0, because you get uh, uh, pre pretty much endless or infinite number of possibilities between the two. Um, this becomes the power of quantum computer, because with less qubits, you can get large computation. In the beginning, they are about the same, but starting having a 3 qubit, you get the required match out of the classical bits is uh, uh, the stage that you can get out of 3 bits becomes 8, and this becomes equivalent to 1 byte. 1 byte is 8 bits. With 4 qubits, you get 16 states, and this is the equivalent of 2 bytes. By the time you reach only 13 qubits, you have the equivalent of 1 kilobyte. This is why a big hope for the quantum computing hardware people is to try to reach the 1 million qubit, because this is going to be a huge number to do calculations with. And they were expecting that using this number, they can break any cryptographic system that the supercomputers may take millions of years to break today would be broken in few minutes or a day or two at the most. By the way, recently they talked about not needing 1 million qubits to do that. I think with the recent advances, they reached a conclusion of only 100,000 qubits. So things are progressing very fast in this direction. And we will talk more in different talks about this area. So when we talk about HPC versus quantum, so some people think that quantum computing is going to be the next step after the HPC. No, it is a next step, but not the next step. High performance computers are going to remain, and quantum computers are going to be integrated with high performance computing computers. This is they are not rivals. They are actually made to coexist, because quantum computers are going to be stronger in solving certain problems, but still HPC is going to be stronger in solving other problems. It is the fear of the world, especially in the area of security, cybersecurity, and cryptography, that the quantum computer is going to be superior to the current. And I put 100 lines under current HPC systems, but future, no, HPC systems are still working on different solutions. But anyway, that nexus between the HPC and the quantum computers, I said before that Japan is working now on the zeta scale, which is the 1,000 computer. But Japan is also working with IBM on the nexus between high performance computers and quantum computers. The idea is we want to exploit the quantum parallelism. You can see here that here we have quantum parallelism on the bit level. So we have a single bit, and it's still able to run multiple states at the same time, as you can see here. This is the nature of quantum computer. With the classical computer, it's either 0 or 1. You get only one state. But here we have infinite number of states, and we can keep doing the calculations with this. Unfortunately, we cannot stop the calculation. We cannot read. We cannot get intermediate results in the middle. But if we wait until the end and repeat the calculation, we can get parallel single qubit calculation. And this is what Japan is working with IBM on. Now, of course, we all hear now about the QPU, the quantum processing units. You can see some small, rather small quantum computers in the market. They are actually affordable. Like this ThinQ computer with 2 or 3 qubits can be in the range of $15,000, maybe $20,000 or something affordable by certain entities. But it is not scalable. You cannot do anything on the production level with it. But the quantum processing units, the QPUs, are actually growing. And as I said, the genesis of joining the quantum with the computer is actually nowadays. Japan is doing now some experiments with IBM on the marriage between the HPC and the quantum computer. So they're actually working now on generating a programming language capable of doing quantum and HPC at the same time. So they are joining them on the instruction level. So they are changing the architecture to get, it is actually based on the Fugaku computer that I spoke about before that ended up at the half exa. Now they're trying to get it to work with quantum with an architecture, instruction set architectures that combine quantum instructions with classical HPC instructions. So you write a single program capable of getting the CPU and the QPU to work together in parallel. So it is not a parallelism on the bit level or the processor level anymore. It is a parallelism on the programming and the computing paradigm level. So at the end, we conclude that quantum computers and HPCs are not rivals. We are not talking about who is better, which is better. We're talking about how to get them to work together to solve problems we are not able to solve today. So they are destined to coexist, and they will work together. And this is what we're waiting for in the near future, not the far future, to have quantum HPCs or HPC quantum computers. As I said, they follow different theory of computation, but not a different theory of computability. What is computable will remain to be computable, and what is uncomputable will remain to be uncomputable by either one. And that ends my talk. Thank you.
Okay, so thanks very much, Dr. Ahmed, for this elaborative and a very clear presentation that highlights the story from the HPC and all the complexity about high performance computing and why would we need it, and international facilities around the world and the challenge to build them until we reach to quantum computing and the clear distinction between quantum computing and between HPC. Now everyone okay is happy. That's really great. Let's receive their questions. So please type your question in the chat. Okay, so I see Noor. Let me just. Okay, Noor. So please, Noor, go ahead. Nouruddin. Okay, you can unmute yourself and ask us a question.
Hello, professors. Can we just go back to the slide about like the number of permutations in the regular bit and the number of also combinations in the qubit, because I didn't quite get that. Like, I think that with 2 bits we can have like up to 4 different permutations, right? Why did we mention only 1? I think it's 28. Yes, 2 bits versus 2 qubits.
Yeah, this is the number of possible states of the 2 bits. When they become 3 bits, there are still two possible states for each one because the bits do not affect each other. In the quantum computing, the bits affect each other. So you do not take the bits separately, like you do not read them one by one as you do here in the classical bits. And this is why with two bits here, it is two states, possible states, 0 or 1 to make the numbers out of. But in the quantum, it can be 0, they can be zeros, they can be ones, and they can be any number in between. That number is going to lean more toward the 1 in some cases and lean more toward the 0 in other cases. So we have 4 possible states.
Okay, thank you, Doctor. Thank you, Professor.
You're welcome.
Okay. Yeah, thanks, Dr. Ahmed, for the answer. Thanks, Noor, for the question. We have another question and comment from Dr. Hisham Al-Mahdi. The calculation of the weather prediction in Egypt. A great example you give us to compare the time needed by a single process and HPC.
Yes.
Okay.
Yes. Yeah, Dr. Hisham, you are welcome. Thank you for attending this. Yes, I gave that before in a different lecture. Actually, there were some different applications in many industries that I gave before, but at this time I wanted to focus on the relationship between HPC, AI, and the quantum computing, and this is why I had to skip many things, including the industrial examples that I will be happy to in a different lecture.
Okay, there is another question from Iman. Could you please explain how parallelism can be achieved when we have to wait until the qubit gets its value, then run to get another value?
Could you read the question again? I'm sorry.
Yeah, the question says, could you please explain how parallelism can be achieved? So she is wondering how the parallelism is achieved when the qubit has some value because of the operation on it, and then this operation is executed, and then the qubit will get another value. So where is the parallelism? She is wondering, or she doesn't see where is the parallelism here.
Okay. The parallelism is actually during the calculation itself. We repeat the calculation because it is of a probabilistic nature. So we want to make sure that we got the right calculation. But when we are doing the original or the first calculation, this is being done in parallel because the quantum computer is running all the possible states at the same time. So even if you have a single bit, this is what we call the single bit parallelism. So the parallelism here is different from the concept of parallelism in the classical computer. In classical computer, we have several processors working together at the same time in parallel. But in quantum computer, the parallelism is done on the possible states at the same time. We do not calculate the 0 and the 1 and make another combination. No, they are being done as they are running. But the payoff is that we cannot stop in the middle. If you stop in the middle, you interrupt the calculation, then you don't have the final result anymore.
So thanks, Dr. Ahmed. I hope
the nature of quantum calculation is going to be clearer, maybe during toward the middle of the school, when you get some hands-on and you do some program and you see how things are running. I think this will become clearer. But at this time, I know it might be a little bit confusing because most people think of the quantum bit as I don't know, maybe some sort of alternative to the classical bit. No, it works in a different way. It's a completely different theory, a completely different technology.
Okay, thanks, Dr. Ahmed. Before going to another question from the chat, we have Sarah. She's raising her hand. Sarah, please go ahead.
Hello. I just wanted to ask, wouldn't we reach a point where we would be in a similar situation such that Moore's law would apply as well, since we would reach like the states of the quantums? Wouldn't we be not able to have more states when we increase the number of bits?
Actually, this is one of the problems the quantum computing industry is working on to increase the number of qubits. But the problem with that is, as I said before, quantum bits affect each other. They don't work separately like the classical bits. So even in a single quantum bit, we have a problem with the coherence, the error correction, and the noise. We have many things, and these problems actually multiply many folds when you increase the number of bits. And this is why the progress on the number of bits is running a bit slow. But the good news is that the industry is always to make leaps, or able to make good progress with the error correction, with the noise, with the coherence, and these things. So this is why until recently, we were hoping to reach the 1 million qubits in order to solve all the encryption problems. And nowadays, I think it was only 2 months ago or so when they announced that they can do that with only 100,000 qubits. So in a way, we are trying to increase the number of qubits in a system. And in another way, we are trying to get better calculation with lower number of qubits on the other hand.
I just meant whether the qubit itself can hold up to this number of states, like literally, or is it just an exaggeration when we say it can hold up to an infinite number of states? Like
no,
we tend to say
yes.
infinity.
This is the nature of it. Yeah, literally, it can do that. Yeah.
Mm-hmm. Okay, thank you.
We try to abstract the answer at the end to mean something to us, because we can also we cannot deal with infinite answers. So we try to abstract the final answer into a humanly comprehensible answer. But by its nature, by the way it works, yes, it is indeed infinite.
Okay, is this a human-defined concept, just as a theory, or I'm sorry if I'm asking too many questions?
No worries, Sarah. We have, as Dr. Ahmed indicated, we have several labs that will come later in the school. So I can understand the confusion. Dr. Ahmed indicated that the confusion can come from the perception of the similarity between both technologies. But we want also to take other questions. So please feel free to ask this question also in the following up sessions, and also tomorrow, where you start to really see this hyperdimensionality of the qubit.
Okay, thanks.
Okay, and can you give me a few seconds just to light?
Yeah, please.
Light on it. It became dark in here.
And then we can read we have 2 more or 3 questions, and then we'll stop from the chat before we go to the break.
Okay, I'm sorry. I was looking at the slides. I didn't notice that it became too dark in here.
Yeah. No worries at all. So we have now. So for Sarah, she will follow. Sarah, you will follow today and tomorrow, and then that will be elaborated, and then you will feel this within the hands-on and so on. So now we have a different question. Yeah, thanks, Sarah, for your question. So we have a question from Walid. In classical computers, we know that a bit is 0, 1 by calculating the voltage. So what do we actually calculate for the quantum bit in order to say it is 0 or 1?
This is the physics of it. I think I don't know if we have in our sessions, are we going to cover some physics of the
a bit.
The quantum mechanics?
Yeah,
okay,
a bit. Yeah.
So let's defer this until we get into the, because this is a question in the physics of the,
Yeah, I've muted. Yeah, that's. Yeah.
Okay, so let's cover this in the introduction to practical quantum computing when we talk a little bit about the physics of it, because this requires the physics
Indeed. So thanks, Dr. Ahmed. There is question. Good evening. I'm curious. You mentioned that QC and HPC are going to cooperate rather than substitute one another. Out of curiosity, how these two radically different models of computations can come to work together and cooperate, and how
Very
this
nice
can communicate.
Very nice question. Actually, quantum computers are superior in certain problems. Like, for example, random number generation. You probably all are able to write a program to generate random numbers. But when you use classical computer to generate random numbers, we call these algorithms pseudo-random numbers. They are not really random number generators. You generate what looks like a random number using an algorithm. If there is an algorithm, deterministic algorithm to generate the numbers, then it is not really random. And this is why it looks like a random number, and we call it pseudo-random number. With the quantum computers can generate random numbers by nature. This is the way it works. You can actually generate actual random numbers. So when you want to simulate something of quantum nature, like you want to simulate a system in quantum chemistry, in quantum physics, in quantum whatever, on the quantum level, the best simulator is going to be the quantum computer. But if you want to simulate a system that is not in the quantum world, the best simulator is going to be HPC. If you want to test the interaction between the two worlds, then the best system would be a system that combines both together.
Yeah, so thanks, Dr. Ahmed, for the answer. So just a quick question from Abdullah Hisham. Can quantum technology be used to speed up the crypto mining process?
Yes, this is one of the strongest areas of quantum computers. The world now is in a sort of a panic, and this was actually one of the motivations we wanted to jump into the quantum world at this time, because quantum computers, when they reach certain levels, until very recently was expected to be between 5 to 10 years from now, but very recently it became only 2.5 years from now, and who knows, maybe by the end of this year it might become next year. The progress is going very fast in this area. Quantum computers are going to break the RSA 2048, which is one of the strongest cryptographic techniques that takes a supercomputer millions of years. It is going to break it in maximum 2 days. The world realized that quite a while ago, and this is why the world started working on what we call post-quantum era, which is developing cryptographic techniques and algorithms that are designed for the post-quantum, after the quantum. So if we have a quantum computer, they would still have difficulty breaking those algorithms. So even though we still don't have that computer yet, but the design of algorithms for that computer actually started many years ago. So the answer is definitely yes.
Okay, so there is a question from Mona about what types of problem can benefit from quantum computing. We have several use cases and also presentations, lectures, and labs during the school where such problems will be highlighted and explained. But perhaps, Dr. Ahmed, if you like to give a short answer for this question.
I actually mentioned a few right now, but as I said, there are many things that the quantum computer is going to be superior to classical computer in solving, but there are still many things that the classical HPC is going to be superior to quantum computer in doing. So the best will be in the future when we combine them together. Again, as I said, the classical computer, the HPCs created what we call today the computational science and data-driven science. In the old days, we used to have theoretical physics and experimental physics, theoretical chemistry and experimental chemistry. But these days are over. Now we do not have the science where you can abstract or model a whole physical system in an equation or two anymore, or similarly in the chemistry, and you cannot even do them experimentally. So the only way to to investigate and to study them in research is to work computationally. You simulate the system and see how the simulation is running according to our calculation and prediction. And most recently, it became even data-driven, where we do not have the theoretical model, we do not have, we cannot afford the experimentation, and we do not even have a computational model. All we have is a bunch of data. So, and from this data, we want to extract the whole science. So in the classical computer world, we are doing this. But when this is done, for example, in the physics or the chemistry, in the quantum world, the best simulator for that is going to be the quantum computer, because it is going to be a quantum computer simulating a quantum system.
Yeah, thanks, Dr. Ahmed. So we have two repeated questions from Mina and Yasser about how quantum computers, if they have infinite number of states, does this affect the amount of energy they consume compared to regular computers? Of course, we are going to have a session about this later on in the school, but perhaps if you'd like to comment on this, Dr. Ahmed.
Yeah, I'll make a very quick comment. Yes, quantum computers and energy until now are not friends. And this is due to a principle in physics called Landauer principle. Quantum computing calculations are not reversible. And Landauer in 61 established the principle that for irreversible processes, the entropy is going to be ever increasing. It will never decrease. And this is along with many other reasons. The reason that most powerful quantum computing today require cryoelectronics. They have to be working in very, very, very low temperatures. So it's not about making the computer itself. It's also about making the environment that the computer is going to run inside. So yes, this is one of the hot areas in research and in the industry to try to get production grade quantum computers to work in room temperature, or at least a little reasonably cooled room temperature with a reasonable power consumption.
Yes, thanks, Dr. Ahmed, for the answer. And please follow again there is upcoming sessions, especially on the third day, where there will be a topic discussing an actual use case of the energy consumption of a quantum computer presented by Alain Chancey. Last question, because we have to go for the break now. For those who want to eat dinner in the half of the sphere in the planet, I know it's too early in Egypt, but yeah, we have a lot of people from Europe and the US and some other sphere who, yeah, maybe that will overlap with the breakfast or the lunch or the dinner. So yeah, we wanted to give them this period as well. So the last question is this would mean for a quantum computer would have the ability to solve NP hard problem efficiently?
I don't think I have a definite answer for that. When we say any NP hard, I would say no. Certain problems, yes, but not any. But my answer for that is not definite. We need to read more, study more about it. Maybe we can discuss it. But NP hard is a mathematical concept that have many applications. The nature of the application is a very important factor in deciding what quantum computer can do and what cannot do. It's not about NP hard and NP complete. So I don't have the definite or a trustable answer for this question, but my guess is that it has to be split. If we are talking about any NP hard, I would say no. But if it would be able to solve certain NP hard, I would say yes.
Yeah. So again, thanks a lot, Dr. Ahmed, for the answers. For those who asked about the quantum noise and what happens at the 0 Kelvin, wait for the second presentation after the break, where we are gonna discuss this. So feel free to drop your question again, and then we can discuss a bit of the physics, what happens in the noise, and so on. So in this session, we are gonna dive deep into the technology a bit. So just hold the breath for 20 minutes, and then we just can have a discussion about those questions as well. So I would like to thank Dr. Ahmed again, and thanks very much, Dr. Ahmed, for giving the opportunity for me to contribute with Cairo University on setting up this nice school, and hopefully that will be a very good cornerstone towards establishing a quantum community, not only in Egypt, but also in the Middle East, and potentially a very international collaborative environment as well.
Thank you, Dr. Taha. Thank you actually for your knowledge and generous contribution to this very important field in Egypt.
Yes, thanks a lot, Dr. Ahmed. And then we are gonna convene at in 20 minutes. So that will be in Central European Summer Time around that will be 7 p.m. and in Cairo that will be 8 p.m. So we meet in 20 minutes. Everyone calculate the stopwatch because of the time conversion issues, and then we convene in 20 minutes.